All right, let's continue on with our calculations here of chapter 18. It's thermodynamics information. It's the second half of this worksheet. We'll start with number 8. Number 8 says, determine the temperature above which the reaction below becomes non-spontaneous using the thermodynamic data given to us in the table below. So we're given a reaction, and if we look at this table, we've got each part of this reaction, each species, and then we have a delta H value and an S value. So if we have delta H and delta S, again, we can sort of use this equation. Delta G is equal to delta H minus T delta S. And what we're going to be doing first is just solving what delta H is and what delta S is for this equation. So we mentioned before that if you have a delta sign, what this really means is that we're going to be adding up all of these delta H values for the products, and we're going to be subtracting from this all of the delta H values for the reactants. Okay, so there's one product here, and that is going to be our silver chloride. So that delta H is negative 127.0 kilojoules per mole. And I'm going to subtract from that the two reactants, the silver, which is 105.9 kilojoules per mole, plus the chloride ion, negative 167.2 kilojoules per mole. Okay, so we can pause for a moment and let you calculate what that number is. Okay, so for this value of delta H, I get negative 65.7, and that's going to be kilojoules per mole. All right, so that's my delta H value. And I'm just going to sort of box that up. All right, now we sort of need to do the same exact calculation for our delta S. So I'm going to do that over to the right here. So our delta S is going to be equal to the sum of all of our products minus the sum of our reactants. Okay, so we're just going to look in this chart. Our product again is 96.11. Now this is joules. Okay, so this is going to be important. This energy unit's a little bit different. This is joules per mole Kelvin. And this is really multiplied by 1 mole. Okay, so those mole units again are going to go away. Then we have 1 mole of silver plus. And then we have 1 mole of our chloride anion. All right, which is 56.5 joules per mole Kelvin. So our delta S here, again, I'll give you a quick second just to calculate what this is. All right, what I got for delta S was negative 34.32, and now this is in joules per mole. So I'm just going to box that up. Okay, so now that I have delta H and delta S, I can plug it into our delta G equation, which is delta H which is in kilojoules per mole minus T delta S. All right, so we're looking for a temperature, all right, at which this reaction becomes non-spontaneous. So I'm going to leave this variable of T here, and I'm going to plug in my value of delta S, but I need to make sure that my units are consistent between delta H and delta S. So my delta S right now is in joules per mole. I need to go ahead and convert that to kilojoules per mole. All right, which means we need to divide by 1,000 to get to kilojoules. So my delta S is really negative 0.03432 kilojoules per mole. Okay, so now what I'm going to do is I'm just going to kind of erase some of this other stuff over here, and we'll talk a little bit about now what it means to try and think about solving for a new temperature where things are going to become non-spontaneous. Okay, so we've got our equation down here, delta G is equal to delta H minus T delta S. What we can think about now is how this value of delta G changes as it goes from being spontaneous to non-spontaneous. So the way I usually think about this again is with a ball rolling down a hill. My ball will roll down the hill spontaneously without any energy being added to it. At some point, if we are moving to it becoming non-spontaneous, we can think about that as a ball rolling up a hill. All right, and what we know is that that doesn't really happen, right? You would have to provide some energy to the ball to get it to roll up a hill. So the same is true for reactions. Reactions will proceed in one direction without any energy, but at some point, if you want to turn it to be non-spontaneous, you would have to do something to that reaction to get it from being spontaneous to non-spontaneous. Okay, so we've got this little graph drawn here. The important thing to know is that there's this midpoint in between the two sides of my hill. So my midpoint here would be a value of delta G is equal to 0. And that's really what we're trying to solve for in this reaction. We're trying to see when delta G is equal to 0, what value of T do we need to give us 0? All right, so we've got negative 65.7 kilojoules per mole minus T, negative 0.03432 kilojoules per mole Kelvin. So I can rearrange this equation and solve for what the temperature is. All right. So I've got these two negative signs here, minus T times negative 0.03432. Those negatives will turn that piece into a positive number. All right, so I'll just sort of rewrite that over here. All right, plus T times 0.03432. All right, so now you can imagine rearranging this equation, making our delta H positive by pulling it over to the left-hand side of this equation. Leaving us just T delta S on the right-hand side. All right, and then we can divide by that value of delta S. So 65.7 kilojoules per mole will be divided by 0.03432 kilojoules per mole Kelvin. All right, so that's equal to my T, and I'll give you a couple of seconds to calculate this. All right, so T is going to be equal to 1914.34 Kelvin. All right, now none of our answers here are in Kelvin. They're in degrees Celsius, so we need to convert from Kelvin to degrees Celsius. So that means we subtract 273 from this number. And when we do that, what we get is we get a value of E for this equation. All right, our next question has a slightly different wording. And so what we'll see is that this takes a slightly different equation to solve. So we have a decomposition of calcium carbonate. Notice you're given a delta G 0, or a standard Gibbs free energy value, of plus 130.4 kilojoules at 25 degrees Celsius. What we want to calculate is we want to calculate delta G. Notice this doesn't have a little circle, so it's not a standard state. Instead, this is going to be a reaction that happens if the partial pressure of carbon dioxide is 0.440 atmospheres. And again, we're given this value of R, 8.314 joules per mole Kelvin. So the equation that we need is we need an equation that relates delta G standard to delta G at non-standard conditions. And so that equation looks like this. So we have our non-standard delta G, and that's equal to our standard delta G plus RT natural log of Q. And again, remember Q, this is very similar to our equilibrium constant, but this is called the reaction quotient. We just have this quotient because we're not guaranteed to be at equilibrium in this reaction. So as long as you know this equation, this problem is going to actually be pretty easy to solve. Number one, if we're thinking about Q, normally you can think about this in terms of partial pressures or concentrations of your substances. Notice in this case, you are given a partial pressure of CO2 of 0.440 atmospheres. All right. We have calcium oxide as another product here, but notice that's in the solid state. So remember, if we are in the solid state, we do not count that in our definition of K or Q. So the calcium oxide doesn't matter. The calcium carbonate doesn't matter. So our Q is really just going to be 0.440 atmosphere. So now we can just go ahead and plug in our numbers. So we have plus 130.4 kilojoules plus R, and again, here's where our units matter. So R right now is in joules per mole Kelvin, so we can divide that by 1,000 and get 0.008314 kilojoules per mole Kelvin times our temperature, which is 25 degrees Celsius, or 298 Kelvin, times the natural log of 0.440. Now remember, your K and your Q, they do not have units. So once we sort of define Q, we don't have to keep that atmosphere unit any longer. So now we can just go ahead and calculate what this value is for delta G. All right, so delta G, once we do sort of all of these calculations, what you should get is a value of plus 128.4 kilojoules. All right, so that would be answer A. All right, so now we can go on to number 10. Notice number 10, this is just going to be another definition type question. In which process is entropy decreased? So again, this would be becoming more ordered. So dissolving sugar, that is going to increase entropy because your sugar is breaking apart. Expanding a gas, if your gas expands, it has more room to move around in, which means it's able to move more freely. That increases entropy. Evaporating a liquid, you're taking a liquid, you're turning into a gas, entropy increases there. And then finally there's freezing water. And because we're freezing, that means we're going from a liquid to a solid. That'll be lowering entropy.